everyone. My name is Marco Pisanu. I am the lead game tech programmer at Remedy Entertainment. I work on AI for the last 15 years or so. At Remedy, I work on the engine team, which is creating a game engine called Northlight. We've provided the Northlight game engine for the Remedy games for the last 25 years or so, and also for all the upcoming games. I worked on a bunch of stuff, some great stuff, some interesting stuff with learning experiences. If you want to find me on LinkedIn, you can pick that one right now. I don't have it at the end, sorry. So what I'm going to talk about in this talk is the HFSMBTH, oh, great. All right, that's no notes, great. The HFSMBTH is the hierarchical finite state machine behavior tree hybrid. This is a classic AI decision-making technique, the finite state machine and behavior tree are. The hybrid is kind of, sort of new. I'm going to be doing a small introduction to behavior trees and finite state machines, just for the people out there who are not aware of them. Probably not too many, but just in case. I'm going to do an introduction of the HFSMBTH. I'm going to abbreviate it the entire time because it's too long to keep on talking about. I'm going to chat a bit about the advantages of creating this hybrid. Some game examples which have AI with behavior trees, and also another game which uses the combination just to compare the two. We go over a high-level implementation of how we implemented this technology into our game engine, and then some future trends. So, some quick onboarding for a behavior tree. Behavior tree is a very old technique. Most game engines still support it or use it in one way or another. It is a hierarchical node structure which contains control nodes which decide which branches of a behavior tree should be executed, and task nodes at the end which actually execute behavior on an AI, like moving and shooting and using abilities and that kind of stuff. Both Unreal and Northlight use something called decorators. They are little segments which you can add to your nodes in order to be more modular. Just having those nodes themselves is not very modular, so adding extra decorators on top makes them more modular. These decorators are things like conditions. Can this branch execute? Or they can be execution themselves, so whenever a node activates or deactivates, they're able to add additional logic to nodes. Behavior trees in general execute from top down, left to right. That's about it. Finite state machines are pretty similar. They're a linked node structure. Like the previous slide, this slide has a graph comparing some engines just for simplicity. The biggest difference between a behavior tree and a finite state machine is that a behavior tree will try to execute what it can inside the graph, while a finite state machine will only try to execute what it can from its current state, so it doesn't reevaluate the entire tree, it just evaluates where can I go from my current state. So what is an HFSMBTH? It is the hierarchical finite state machine behavior tree hybrid, a combination between a finite state machine and a behavior tree. Before I continue, I wanted to briefly talk about the history. It's not a new concept, we didn't invent this. This has been implemented in some engines before, or in other systems like animation systems, and even outside of games as well. But I wanted to bring it here just to show you how nice of a system it is once implemented. I also want to acknowledge some people who've talked about it in the past, specifically a guy called, I had the name, but Bobby Anguelov. He did talk at GDC in 2017 on the AI Summit. If you want to know more in depth about HFSMBTHs, that would probably be a good talk to check out. So why even an HFSMBTH? It comes from a need for improvement. So just having a pure behavior tree for your AI implementation or your AI behavior is kind of chaotic. Like you get gigantic branches, and they're kind of hard to manage. And we found that our designers were using state machines inside these behavior trees anyway. Even though they didn't have the finite state machine capability, they would still try to limit the branches of a behavior tree to go directly to other branches. They wanted an idle state for your NPCs, a shooting state for your NPCs, and then a searching state for your NPCs. But inside the behavior tree, they never wanted idle to go directly into searching. They wanted to go from idle to combat to searching, and implementing that inside of a behavior tree, well, it's not what it's meant for, but they still made it anyway. So you get a lot of messy and chaotic structures. Creating this hybrid does give us better performance on the CPU as well, so that's a plus because of the nature of finite state machines before, where they don't evaluate every single thing, they just evaluate their next steps, means that if implemented at a high level, you have less branches to try and resolve. Some further about why combining behavior trees and finite state machines together is beneficial. We do keep the flexibility of behavior trees. Don't get me wrong, those things are great. They're great for what they are, behavior trees, behavioral execution. They're not so great for control flow. So if we introduce that together with a finite state machine, we still get the cohesiveness of a finite state machine. Cohesiveness being like, it's very easy to reason about it, to be like, where does it go next? Something you don't have in a behavior tree. It can go anywhere. Combining those creates, sorry, 1 second. Creating those together creates enhanced AI behavior control. Because of the FSMs and behavior trees combining together, you can segment them more. You can take that control flow and that behavioral flow and segment it better. Because they're segmented better, it becomes more readable. And also because it's more readable, it's more debuggable. Someone can come in, realize like, oh, this is how it's supposed to flow because you have subtracted these or separated these pieces of logic from each other, and so it's easier to reason how should it flow and why isn't it flowing like this. Oh, I went one too far. Can I go back? Yes, there we go. We're going to talk about control. This is a game which Remedy developed in 2019. It is a action-adventure third-person shooter where you go through a supernatural and paranormal game world, fighting lots of enemies in groups and also the occasional boss battle. It was AI done purely in behavior trees. So for the next few slides, I have some examples of production content which we shipped the game with and why these things actually mimic behavior trees. This is not going to be very readable. It doesn't matter too much that it's not readable. I realized it was down, so I moved it up. But what's important about this slide is to understand that all those tiny pink nodes in the bottom, they're states. They are states inside a finite state machine which the designers implemented just in this behavior tree. The lower left, for example, has things like throwing grenades, going berserk, and some other abilities. The middle has idle behavior, shooting, searching behavior, and the right side in the bottom right has cover behavior. As I mentioned before, we don't want these to be able to go from every state to every other state. The behavior tree allows that, so it's hard to reason where can we now actually go. So that's why it's a finite state machine implemented inside a behavior tree. It's not very readable. Another example is boss phases. Boss phases are a great example of why you would want to use a finite state machine instead of a behavior tree. Here they did it as a behavior tree. They decided that the big red group over there would be when the boss was in a room with the lights turned on, and the blue one would be when the lights would turn off. They didn't want to just arbitrarily be able to switch between the two of them. Once the lights are off, the lights stay off. There's no need to go back. But the behavior tree will still try to evaluate it. And lastly, probably the most important use case for us was cover flow. Cover flow is a very rigid feature in video games, usually. The usual flow for cover goes that you find a position where you want to go in cover, you go to set cover, you get into your animation for being in cover, and you start doing stuff in cover. While you're in cover, you don't want your behavior tree to just randomly flip somewhere else and go like, ha, we're gonna throw grenades now, because that's not supported from cover. Additionally, you need to exit cover. Just starting a new move to go somewhere, you're still in cover. You need to execute an animation to go out of cover. Because it's so hard to force the behavior tree to follow this flow, you have to go from this to there to that. We had a lot of issues with animations not really lining up because we didn't call this exit from cover node inside of our behavior tree. The behavior tree just switched to movement. So this meant that in our C++ runtime code, we had to create a lot of hard-coded, hacky code to check, did we leave cover? And if so, first inject this other movement ability to exit out of cover again. I don't like that kind of hacky workaround code in our code. And it also means that when we have that hacky code, it means the designers lose control over what to do. We now randomly decided to exit cover because we got a move to node, but maybe that's not what the designers wanted at all, and it should have errored, but it doesn't anymore. So that was control. The next one is Alan Wake 2. Alan Wake 2 is a game we shipped last year. It is the sequel to Alan Wake 1, which is all the way back from 2010. And we created Alan Wake 2 using the HFSMBTH. Similar to Control just now, I have a few slides detailing the exact same scenarios, but then using a HFSMBTH. So this is combat states. Compared to the graph we saw before, this is infinitely more readable. You can easily reason from the middle state, where do I go to? You can also easily determine that all the way from the left state, I'm not immediately able to go to the right state, which is something which was severely lacking in our previous big chaotic behavior tree. Boss phases, likewise, a lot simpler. This is probably the simplest example we have. On the left side, we still have a behavior tree. Due to legacy reasons, all of our enemies still require a behavior tree to be their first initial behavior tree. But because this is a hybrid, the pink node at the bottom immediately references a state machine. This state machine has 3 boss phases, but interestingly, the connections between the states, which are the teal, I guess, nodes, they only have one condition, which are those decorators over there. Just having one condition usually isn't enough to switch between boss phases. Usually you want like more conditions to switch between boss phases. But in this case, there's only one, and that's because the designers have decided to put the conditions of switching between boss phases inside the behavior trees of the phases. That shows that the designers did really start using finite state machines, but they didn't really take full advantage of it yet. So I hope they catch up to that in a bit. And the reason why it's not full advantage is because those behavior trees inside the phases now can't really be easily reused anymore. Inside those behavior trees, they set the conditions of when to go to the next phase, and the finite state machine will react to that, which is not great for segmentation. These are the behavior trees for the boss phases. As you can see, these are simple, segmented. They just do those few branches, and there is no more pink nodes over here referencing even further. They are the leaves of the bigger graph. There's still one pink node, but that's okay. This is the third boss phase, just as an example of that. For behavioral control, we still use behavior trees. And then our cover flow state machine. That was our biggest worry, really. But I do have to preface this that This does not come from Alan Wake 2, and that's because Alan Wake 2 did not have cover. But hopefully when we create games again with cover, they will start using this kind of state machine because it solves our issue of designers not having control over their entire AI. I had more, but alas. So onto our implementation then. FSMs are really very similar to behavior trees if you look at it from an implementation point of view. They're both node graphs, they both have children, they both have decorators on those children in our implementation anyway. But the main difference for our implementation of a finite state machine being different from a behavior tree is that our finite state machines do not have execution logic. They are purely state handling. So where the behavior tree has all these things like start moving, start shooting, and all that kind of stuff, our finite state machine doesn't have that. We chose that because if we would have allowed the finite state machine to also do all this task handling, this execution logic, our finite state machines would bloom again into the same kind of chaos we were trying to get away from before. So since they're only states, those states only reference other graphs, which is the hierarchical part of the HFSMBTH. All those pink nodes, they reference other graphs. Those states can reference other finite state machine graphs, but they can also reference behavior tree graphs. In the end, that means that you will always find behavior trees at the bottom because finite state machines can't execute logic and you need to execute logic at some point. So a little bit about how we actually did it on the data side and on the runtime side. We created a base HFSMBTH implementation of a standard node graph. These node graphs are just a collection of nodes, and nodes can be connected to any number of child nodes. These nodes decide which child to execute and how. And that's pretty much it for the base. They share a bunch of other standard implementations of graphs, but it's not too relevant for this talk. Building onto that base implementation of a graph would be a behavior tree specialized part. A root node would just be a traditional graph node, and it would execute its children left to right on our editor, but top to bottom in our data layout. Selector nodes are a standard node for behavior trees. They would pick the first child which would meet its conditions to execute, and it would start executing them. And similarly, the parallel nodes just picks all of the children which can execute and executes them. And the finite state machine is implemented in the same way. It evaluates its children, which is the outgoing state transitions based on priority, and it changes the state based on which connection will, on the first connection, which meets its conditions. Yeah, great, English. I have a small overview of this entire thing in action. So we have a little sneak peek at our internal tools. On the left side, we have our level editor, and on the right side, we have the behavior tree and finite state machine hybrid in action. I'll talk a bit more when it plays. Yeah, there we go. So our engine for debugging will show all the nodes which are active. All the orange nodes are either states in the state machine or control nodes in our behavior tree. The green ones are actually executing logic. The top left one is our initial behavior tree, which I mentioned before. The lower left one would be our awareness state machine, which is currently in combat. The upper right finite state machine would be our combat state machine, which will alternate between moving and shooting, and standing and shooting, as you can see on the video. And the bottom right corner is a behavior tree for moving and shooting. So as you can see, while it's moving, it's lit up. And while it's standing still, another behavior tree, not shown here, will be executing. And this is how our designers work with it. So with all that in mind, our conclusion at the end, after shipping Alan Wake 2 and continuing to develop our new games with this same tech, is that an HFSMBTH is definitely better at flexibility, readability, and scalability, just because of how the content setup can now be more easily divided and more easily be read. But it does come with some drawbacks. Just a regular finite state machine or a behavior tree, it is simpler. You don't have to reason about where do I put all my logic? Do I put it in a finite state machine? Do I put it in a behavior tree? And people are usually already known with either of those two. So onboarding has become somewhat of an issue for us because we tend to find people who know behavior trees. We tend to find people who know finite state machines, but we don't tend to find people who have combined them before. So we shot ourselves in the foot a little bit with that one. It works well with skilled people. If you have skilled technical designers, then this should be no problem for them. If you already understand both systems, it's not the worst to reason about it and combine out of this. As I have shown before, it led to better content setups. We have better segmentation and readability. And debugging is easier, as you saw with all the fancy coloring. All in all, it was so far worth it for the Northlight game engine at Remedy. Just because we made something better, though, Just because we made something better, though, doesn't mean that we're done. Maybe we will get the HDNBTUSGOAPH? Yeah, probably not, but hey, who knows. Goal-oriented action planning, hierarchical task networks, and utility systems are, all in all, still a great way to do AI. And it might be useful to see if we can hybridize those into it as well. Goal-oriented action planning and hierarchical task networks are both great for either behavioral control or control flow, so you can kind of try to merge this in anywhere, but personally I'm most interested in utility systems. Behavior trees are still great for behavioral execution, but a lot of people prefer utility systems as well. So we'll probably start looking into trying to create a hybrid where we can put in a utility system as a reference inside a finite state machine instead or together with a behavior tree so that our designers have more flexibility and have more options. That was somewhat shorter than expected, but I probably missed a few things. Anyway, thanks for listening, and if you have any questions, now would be the time.
Yeah, guys, any questions?
I'm assuming you know Unreal, how it works.
Somewhat. I'm not really an Unreal developer, unfortunately.
Okay, so with this combined hybrid system, are you able to connect your animation graphs to your behavior tree finite state machine hybrid easily?
Connect in what way?
Like sync up your animations with your hybrid of FSM and BT.
Yeah, so for Northlight, we have segmented and separated our animation graphs and our behavior trees with our own independent layers, so to speak. The behavior tree and finite state machines don't immediately interact with animations because the finite state machines and behavior trees can respond very fast. Like they can twitch and do things in a matter of frames, and you don't want your animations to just start twitching because of that. So we have an intermediate layers of things we call programs for the AI. The behavior tree will steer those programs, and those programs will decide whether or not the behavior tree is even allowed to interrupt them or not. Like, for example, if you're already in a stopping animation, they won't be allowed to interrupt. And our animation graphs interact with those programs instead of with the behavior tree.
Okay, so like let's say both are contradicting each other. Animation is going in one direction and your behavior tree is trying to take it in some other way. Which one do you prioritize?
We prioritize our behavior trees. Our AI decides what we're going to do, and our animations try to follow along with it.
Yeah.
All right, guys, who's next?
Hello. So I found the HFSMBTH really fascinating. So I was thinking like, did Remedy plan to use any neural networks or genetic algorithms to like make generative AI logic?
We've talked about it. Probably not for the near future. The biggest reason is that the games which we make at Remedy are very hand-tailored. If we're going to use generative AI to either make a generative AI node, which we can call from the behavior tree, or use generative AI to even generate these trees, our designers will probably be like, we don't have direct control over this. Our bosses and our enemies, they're, as I mentioned, very hand-tailored specifically to the situations we put them in into our games. So for our games, probably not, but I can see how that would work for other games.
So like the bosses are literally scripted to do what they are told to do.
Yes.
Okay, thanks. Thank you so much.
You're welcome.
Who's next?
Are there any drawbacks in terms of performance one can expect when using this hybrid when compared to standard state machines and behavior trees?
If you're just using standard state machines, the behavior tree will in generally be slower than a standard state machine. So if you're just using finite state machines right now, this will give you a small performance impact on the CPU because of the way how finite state machines have to evaluate all their branches. If you're already using behavior trees, this will save you CPU time. On the memory side of things, it doesn't matter too much. They're both node-based systems.
Thank you.
Anyone else? Guys, we actually have time for questions.
We have 20 minutes. My talk was a bit faster than expected. Sorry for that.
Hey, so according to you, the main differentiator why studios don't use this is the skill gap, right? Because
I'm not sure if it's the skill gap or if it is just not knowing about it. Like, I didn't really know about this before until I actually started implementing it. And then when I started implementing it, I started doing research to it. So I think it might just be that it's not widely known enough about how nice of a system it is, in my opinion.
yeah, the way you explained it, like slide after slide, it just started clicking how these things are actually quite modular and sensible.
Yeah.
So I would like to ask, why aren't studios like maybe Naughty Dog or Rockstar implementing this, or maybe they are already?
Maybe they are. I don't have a look at their internal tech, unfortunately. I hope they do. I think it's a nice system, but I don't know why. I know Unreal is going somewhat away from behavior trees, if I'm aware, but I'm not an Unreal person, so I wouldn't know. I don't know what their next steps are, but it'd be interesting to see what they do.
Okay, thank you so much. Just one last thing.
Sure.
What would be the drawbacks, in your opinion, of using this system apart from the logic that you have to think about while crafting it?
The learning curve, definitely. Like, it took our designers quite a bit of time to be like, okay, how do we transform our behavior trees into these finite state machine stuff? If they would have just continued using behavior trees, they, well, wouldn't have that hiccup of the learning curve. So, yeah.
Okay, thank you so much for your time.
Hi. First things first, I want to thank you so much for this talk. It was really great, and for wrapping up so quickly. It was really a lot. It gives a lot of time for Q&A. You had just mentioned that it's not widely known, this behavior trees, in a way at least. Are there any recommendations you can give for researching a bit more into it and places where they can be implemented a little bit more, in the spare time or anywhere else?
So, in my personal research, I used Bobby Anguelov's talk about this specific topic, but then for animation side, on the ICE Summit at GDC of 2017, he goes a bit more into detail. So if you want to research this topic more, I'd recommend checking that out. There's also a paper from 2023 where they applied it to robotics outside of gaming, which might be interesting as well. If you search for HFSMBTH, you can get some results.
Good evening, sir. I'm from AI/ML background, BTech background. The question I had is mixing two frameworks into an application. It is complicated. You have to remodel your data set. You have to, even if the necessity is less, but it creates a complexity when you use two frameworks. How do you handle your model?
So in our case, we were lucky. We had a behavior tree system which was set up in such a way that implementing a finite state machine into it was somewhat trivial. So we didn't really have to create two frameworks. We already had a node-based system which allowed children and which took those children and asked it, what is your next step, which is part of the behavior tree. Finite state machine is identically the same. You go from a state and you ask your connections which part can go first. So it's not necessarily two different frameworks, it's just a slight abbreviation and abstraction of the framework.
What are the hardware and software components are you using in your project?
Sorry, say that again, please.
Hardware and software components, the requirements.
The requirements for what, sorry?
Hardware components or software components.
Sorry, I don't think I understand the question.
Okay, sir. Thank you, sir.
Okay, sorry. If you want, I'm going to be here afterwards if you want to elaborate your question. Sorry.
Hello, I'm Ishant, and I actually wanted to inquire to you about Horizon Zero Dawn. I saw you worked on it, and so I wanted to ask you about its combat system. As you know, like there are like variety of enemies in Horizon Zero Dawn: Trampler, Stalker, and there's even a creature which can drill into the land, right?
The crocodile thing.
Yeah, like and like. How did they manage to make it so seamless? Was it difficult? And how different is it from, the workflow that you have at Remedy?
So, that's a good question. And I don't think I have a good answer for it. Like, it was mostly the gameplay designers who did that. I was a junior AI programmer at that time. I didn't really get to interact too much with how seamless they made the combat. I was responsible for 2 of the robots in there and the environmental NPC system, so unfortunately I can't answer that question.
Okay.
Hi. In the beginning, you talked about control, and since we were talking about behavior trees and finite state machines, and as you guys didn't have the time to implement like a hybrid of both, you said that you used a lot of hacky code inside of it, right? So I just want to know, like, what is the priority when the release schedule is nearby regarding these things? Is sort of refining the control flow or the process flow more important, or is the release schedule more important that we sort of...
The release schedule is 100% more important. I can hack my code any way I want as long as I make my release schedule. Like, if the game ships in 2 weeks, that's what's going to ship for sure. Yeah, sorry.
Yeah. Have you worked on projects where the process just worked out and there were no hacks specifically, like to a very large scale? Does that ever happen, or does it always end up being in that state for larger projects? There's always some hackiness. You can't, well, I haven't seen someone escape the hackiness yet of trying to launch a game. This kind of stuff where we had to hack around with the exiting of the cover state came not late, but not very early either. We realized we're not going to be able to create an entire new framework within the time in order to solve this issue, so we need to hack it. But if you go closer and closer to releasing a game, there's going to be a lot of hacks, like a lot of hacks. Thank you. You're welcome.
Yeah, hello sir. I wanted to ask, I follow Remedy on LinkedIn, and I see you hire interns also. So
Sometimes.
yeah. So let's say somebody is from Unreal or Unity background. Then how long is the learning curve to get into Northlight engine?
The Northlight engine is at the moment, pretty modern take on an engine. People have said which interns and other juniors and seniors which have come into Northlight and started using our new tech, which is about 2 years old now. We had some older tech before. They say they really like it and they can flow into it very easily.
So what are the basic skill set a new person should have already to get into that state, to be able to be at Remedy and get to that level?
Well, that really depends on which role you're applying to.
Programming.
Programming role, basic understanding of C++, and a good knowledge and a history of implementing the tech which you're applying for. If you're applying for an AI role and you're an intern, first of all, you'll get a test, but second is that on your portfolio, we would like to see that you have implemented like some sort of tech which we use. Like we use we use behavior trees and finite state machines. We also use a bunch of nav mesh generation and things and path steering. If you implemented one of those from scratch, that's a great start.
We have time for one more question.
Elaborating on what she said, I think I got what she was trying to say. Maybe I didn't. I'll just ask around.
Sure.
Given that Remedy or Northlight is in proprietary engine, right? So using HFSMBTH is technically something that not everyone can do, is what I'm trying to say. It's a technique that I get across, but if one were to try it for their own or their personal projects, how would one go about it? That's what she was trying to ask. Maybe then she was asking components altogether.
How would you go about it? I mean, it's pure C++. Write code? Sorry, it's not the great answer, I know. If you want to implement something like this in Unreal, you have to write your own editor, either externally from Unreal or internally. They already have their behavior tree editor. I don't know Unreal, but I hope they have their source code available for that. It shouldn't be too hard to augment that because it's just a node-based system. Yeah, I don't see anything stopping anyone from using this. Even though this is proprietary, almost every engine out there will have some sort of behavior tree implementation or finite state machine implementation or node graph system in that sense. If you have that, you can implement this.
Absolutely, thank you.
Welcome.
Hi, I had two questions. One thing just to add on to what people are saying. Unreal does have something new that they have just introduced called state trees, which probably you can combine with behavior trees or tasks to do some mixing of both types of system. My question was generic. Since you said that you have updated your old behavior tree system with new upgrades, as a studio, when do you decide that, okay, this is a time for us to upgrade the systems, which would give us a better control over game mechanics, AI, and things like that? So at what time?
It all depends. It's a great answer to every question, but more specifically, the way we work on the engine side of things is that we provide our game teams with our engine. We take requests from the game teams, and whenever we do, we make their tech. Sometimes we have enough time to do R&D, and during that time, we create stuff like this. So whenever the game teams don't have an immediate pressing need for us to go in and please create this thing immediately for us, if we have a bit of time before they need their new systems, we go in and we try to improve the workflows, create new systems, and that kind of stuff. We will not do this kind of things while games are shipping. Doing this while games are shipping is a bad idea. So this one started off probably a month or two after Control shipped and the game for the team for Alan Wake 2 was in pre-production.
Just to add on to the same question. So when you say you have downtime and you build up new stuff without requirements, based on your experience, what is a good place to look for these kind of things? Like if somebody wants to improve the system, where do they go find resources that these are the things?
GDC talks, yeah, that's usually the way to go. We also have just direct contact with other studios. So we can go in and ask them like, hey, what are you doing for AI? Oh, that's cool, let's just steal that, come on. They steal stuff from us, it's fine. So it's a give and take, but that's why we have GDC talks, right, to share this kind of stuff. So those two ways. The other way is, of course, also looking at papers which have been written outside of gaming. As I mentioned before, the HFSMBTH has been used in robotics because of our talks in gaming, and we can apply that the other way around as well if we find a good topic, but it's probably a bit harder to shift through those research papers.